Hi friends, welcome to the lecture of Advanced Discrete Mathematics. Today we are going to study a new concept which is a principle of inclusion exclusion. Inclusion exclusion. Okay, now we have to see what is the principle of inclusion exclusion. Let A and B are any two finite sets. Let A and B are any two finite disjoint sets. Okay, finite disjoint sets. Then cardinality of A union B is equal. That is, suppose this one is the whole universal set X, which contains two sets A and B. This one is A, and as they are disjoint, then there is no element common between these two sets. This one is A, and this one is B. And suppose A contains some M elements and B contains some N elements. Then cardinality of A union B is nothing but M plus N. Therefore, cardinality of A union B is nothing but cardinality of A plus cardinality of B, which is true whenever A and B are two finite disjoint sets. Okay. Similarly, if suppose this one is the first one, and second one, if A and B are again to any finite sets, then cardinality of A minus B is equal to cardinality of A minus cardinality of A intersection. Okay, if suppose A and B are any two finite sets, then cardinality of A minus B is nothing but cardinality of A minus cardinality of A intersection B. Now, the set A can be written as, here also set A can be written as A minus B union A intersection B. Let us take these sets. Here is A, this one is B. This set A, this one is set B, union set X. Then cardinal A can be written as A minus B union A intersection B. Now, A minus B and A intersection B are two disjoint sets. A minus B is nothing but this part, and A intersection B is nothing but this. So, union of these two sets is nothing but A. Now, as they are disjoint sets, there is no element common between these two sets, that is A minus B and A intersection B. Then by previous one, cardinality of A is equal to cardinality of A minus B plus cardinality of A intersection B, which implies cardinality of A minus B is equal to cardinality of A minus cardinality of A intersection, and which is again from the this one, and hence the okay. Now, if suppose A and B are in not a disjoint sets, then what is its value? Okay. Third one. Let A and B are any two finite sets. Are any two finite sets. Then we have to prove that cardinality of A union B is nothing but cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay, now let's see. We said A union B can be written as, here A and B are not disjoint sets. This one is A, this one is B, this one is the universal set. Yes. Okay. A union B. A union B is nothing but A minus B. A minus B is nothing but this part. And union is set B. That is this part union this one. That is this one. Okay, which is nothing but A union B. Again, this A minus B and B are two disjoint sets. Then from the this one, if A and B are into finite disjoint sets, then cardinality of A union B is equal to cardinality of A minus B plus cardinality of B. But from second one, cardinality of A minus B is nothing but cardinality of A minus cardinality of A intersection B. So cardinality of A minus cardinality of A intersection B plus cardinality of B. Cardinality means the number of elements belonging to that set. It's called cardinality of that set. Which is nothing but cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay, this one is the cardinality of A union B. By Venn diagram, this can be represented as this one is the set A, this one set B, this is the A, B, and this part is nothing but A intersection B, and whole is nothing but its union. Okay. Now, how the number of elements in A union B are the number of elements in A plus number of elements in B minus number of elements in A intersection B. Let us see from the Venn diagram. Actually, now if we have to find out the cardinality of A union B, if we take cardinality of A, cardinality of A contains all the elements in set A, number of elements in set A. Therefore, these elements, that is the elements in A intersection B, are added one times in cardinality of A. Now, plus cardinality of B. If we take cardinality of B, that is the number of elements in the set B, then the elements in A intersection B are added second times. But if we take cardinality, then we take the sum one time only. As these numbers are added two times, then here we have to remove this one in one time. That is, this part is added in A also and B also. Therefore, here we have to remove the middle one part one time. Therefore, which is nothing but minus of A intersection B. Therefore, which is totally nothing but the cardinality of A plus cardinality of B minus cardinality of A intersection B is nothing but the total number of elements in the set A union B. Those elements are subtracted which are added two times. Okay. Now, similarly, we have to find out the cardinality of three sets. That is union of three sets. Then cardinality of A union B union C is equal to. Now we know the method to find out the cardinality of A union B, which is nothing but cardinality of A plus cardinality of B minus cardinality of A intersection B. Let us take this B union C as a D, which is equal to A union D, where D is nothing but B union C. Now again, cardinality of A union D is nothing but cardinality of A plus cardinality of B minus cardinality of A intersection D. Now put the value of D. Cardinality of A plus D is nothing but cardinality of B union C minus cardinality of A intersection B union C. Okay, which is nothing but cardinality of A plus cardinality of. Now again, cardinality of B union C. From this one, which is nothing but cardinality of B plus cardinality of C minus cardinality of B intersection C minus of cardinality of A intersection B union A intersection C. Now, which is nothing but cardinality of A plus cardinality of B plus cardinality of C minus cardinality of B intersection C minus. Okay, take the minus outside. Now, A intersection B union A intersection C. Let us consider this one as a set F and say this one as a set G. Therefore, cardinality of A union B, that is cardinality of F union G, is nothing but cardinality of F plus cardinality of G minus cardinality of F intersection G. First, we have to take the cardinality of A intersection B plus cardinality of A intersection C minus cardinality of A intersection B intersection A intersection C and the whole cut. Okay. Which is nothing but cardinality of A plus cardinality of B plus cardinality of C. Okay. Minus this plus one is take outside, then which is nothing but cardinality of minus of cardinality of A intersection B plus cardinality of A intersection C plus cardinality of B intersection C, and this minus 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 plus, and A intersection B intersection A intersection C is nothing but A intersection B intersection C, which is nothing but A intersection B intersection C. So this one is the cardinality of the union of these three sets A union B union C, and which is nothing but cardinality of A plus cardinality of B plus cardinality of C minus cardinality of these two sets intersection of these two sets A intersection B plus cardinality of A intersection C plus cardinality of B intersection C plus cardinality of A intersection B intersection C. Let us see this one by Venn diagram. Suppose these are the three sets A, take this one as set A, B and C, which is nothing but A intersection B. This one is nothing but B intersection C. This one is nothing but A intersection C, and this middle part is nothing but A intersection B intersection C, which is common in all the three sets. Okay. Now here from this Venn diagram, cardinality of A union B union C is equal to cardinality of A plus cardinality of B plus cardinality of C. Okay, now if we add the cardinality of these three sets, then this part is added. This part is added two times in cardinality of A also and in cardinality of B also. Again, this part is again added in two times. Okay, in A and C respectively, and this one is again added in two times. That is, these parts are added two times. Then here, if we take the cardinalities, then the cardinality of this A intersection B is added two times. Then we have to subtract one times. Therefore, minus cardinality of A intersection B plus cardinality of A intersection C plus cardinality of B intersection C. That is, this part is we have to remove. Those parts we have added two times. Then we have to subtract it from the this one to one time. Okay. Now this part, that is A intersection B intersection C. Okay. This one is added first three times. That is in A, B, C both. So this one is added three times. Okay. It is present in A, present in B, and present also in C also. Therefore, this one is added three times. And when we remove cardinality of A intersection B, then this one is the A intersection B. But when we remove this one, then this one is removed. That is A intersection B intersection C. That the common part is also removed, which is also present in A intersection C. So here also that is removed. And similarly in B intersection C. If we take B intersection C, then also it is present, and when it is removed, then it is removed from this total sum. So first of all, this A intersection B intersection C part is added three times and subtracted three times. Therefore, there is no element from this in this sum. Therefore, here we have to add this part again. Since here we first added 3 times and subtracted 3 times, therefore this part is not in the cardinality, therefore we have to add it, which is nothing but cardinality of A intersection B intersection. So in this way we can find out the cardinality of the union of any number of finite sets. Okay. Now, for the principle of inclusion exclusion, why the name inclusion exclusion is given? Okay, let us see it. Let us here note that cardinality of A union B union C is nothing but cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B plus cardinality of A intersection C plus cardinality of B intersection C plus cardinality of A intersection B intersection. Okay. Now here we have to see why the name itself name is given principle of inclusion exclusion. If to find the cardinality of the union of sets, we first include the cardinalities of the sets. Cardinalities of the set. So from this one, let us see. To find out the cardinality of A union B union C, first we include it, the cardinality of each sets. So here first we include. So there is some part common in these cardinalities. Then we have to subtract it. That is, in second condition, exclude the cardinality of pairwise intersections. Okay. So here we have to exclude the cardinality of the pairwise intersection. In third one, include the cardinality of triple wise intersection. Okay, that is triple wise intersection is included. Similarly, this is for 3 sets. If there are more than 3 sets, then fourth one is exclude the cardinality of quadruple wise intersection. Okay, and again in fifth one we have to include the cardinality of quintuple, that is fifth one, quintuple wise intersection. Okay, so continue in this way until the n tuple wise intersection is included if n is even and excluded if n is odd. That is, if the number of sets are even, then we have to continue the n double wise intersection up to including. And if n is odd, then we have to exclude it in the last step. Okay, that is for any two sets A union B. We have the last term is excluded, that is minus of A intersection B. But in third one, that is if there are three sets A, B, C, then cardinality of A union B union C. In last step, we have added the its cardinality of A intersection B intersection C. Therefore, here we have to first include the cardinality of all the given sets, then exclude the cardinality of the pairwise intersection, again include the cardinality of the triple-wise intersection. In fourth one, again exclude the cardinality of the quadruple-wise intersection, and fifth one, include the cardinality of the quintuple-wise intersection, and so on. So here we have included and excluded the cardinality of the sets. Therefore, from this method only the principle has given the name of principle of inclusion exclusion. Okay, this is for three sets. If there are n sets, then in general in general for n sets a1 a2 up to so on an, cardinality of union I running from 1 to n ai is nothing but summation 1 which is base equal by I which is base equal by n, cardinality of each ai, okay, minus summation 1 which is base equal by I which is base nj which is base equal by n, cardinality of ai intersection aj plus summation 1 is equal by I less than j less than k is equal by n, cardinality of ai intersection aj intersection ak plus up to so on minus 1 to the power n minus 1, cardinality of a1 intersection a2 intersection up to so on intersection. Yeah, this is for the n sets. Okay, now we have to see what is the actual meaning of principle of inclusion exclusion. There is an alternate form of the principle of inclusion exclusion. There is an alternate form of the principle of inclusion exclusion, which is useful in counting problems. Okay, counting problems. If suppose there are n properties, if there are n properties which are nothing but p1 p2 and up to so on p, that is p1 p2 up to so on pn are n properties. Let pi1 pi2 up to so on pik be k properties from these n properties. Okay, So these are the K properties among these n properties. Let capital N of P1, P2 up to Pi1, Pi2 up to so on Pik denotes the number of elements, with the properties Pi1, Pi2 to so on Pi. Okay, now if the number of elements, the number is this is from this symbol denotes the number of elements with properties Pi1, Pi2 up to so on Pik. Then in terms of sets, which can be written as n of Pi1, Pi2 up to so on Pik is nothing but. Here we have to take all the properties at a time. So here we have to take its intersection of these properties. That is those sets which are of these properties. Let us take AI1 is the set with property Pi1. AI2 is the set with property Pi2 up to so on AIK is the set with property AIK. Then if n of Pi1, Pi2 up to so on Pik denotes the number of elements with these properties Pi1, Pi2 up to so on Pik at a time, then we have to take the intersection of its corresponding sets. Then which is nothing but AI1 intersection AI2 intersection up to so on AI. Okay. Now, if the number of elements in the set are denoted by n, are denoted by capital N, then n of P1 dash, P2 dash up to so on Pn dash is nothing but n minus n of P1, that is cardinality of A1 union A2 union up to so on union En. Okay, where n of P1 dash, P2 dash up to so on Pn dash denotes the number of elements with none of the properties P1, P2 up to so on Pn. Okay, none of the properties means the number of elements which are satisfied none of the properties among these n properties, that is the elements which are not satisfy any one of the properties in these n properties. Therefore this n of P1 dash, P2 dash up to so on Pn dash can be written as this n, and we know that how to find out the cardinality of union of n set, which is from the general formula, which is nothing but minus of n of summation I running from 1 to n, that is which is less equal by n, and this one is less equal by I of n of Pi plus summation 1 less equal by I less than j, which is less equal by n of Pi Pj. There is no comma in between these. Okay, Pj. Again minus summation 1 less equal by I less than j, which is less than k, which is less equal by n of Pi Pj Pk and up to so on plus minus 1 to the power n of P1 P2 up to so on. So this one is the another method to find out the cardinality of the union of the sets or this one is the another form of the principle of inclusion exclusion. Now we have to see some examples depending on this definition. Okay. Use the principle of inclusion exclusion. Find the number of primes less than 100. Okay, so here we have to find out the number of primes less than 100 by using this principle of inclusion exclusion. In number theory, we have seen if any composite integer is divisible by a prime not exceeding its square root, that is by in sieve of Eratosthenes. We have seen how to find out the number of primes less than some number. Okay, now according to that, we know that the composite number is divisible by a prime not exceeding its square root. Okay, square root. In sieve of Eratosthenes, we have taken first for n equal to 100 and we have taken the primes less than 10, which are nothing but 2 3 5 7, and eliminate all the remaining elements which are multiples of these 2 3 5 and 7. That same concept here we have to use. Okay, as here 100 is given, and 100 is a composite number, then this composite number is divisible by a prime not exceeding its square root. If we take the square root of 100, then which is nothing but 10. Okay, therefore the composite number 100 is a number which is divisible by prime not exceeding 10. Therefore 2 3 5 and 7 are the only primes which divides 100, which is from this above statement, and which you will have already seen in number 3, which divides 100. Okay, now let pi, whenever I running from 1 2 3 4, denotes the number of elements or the elements divisible by 2 3 5 and 7 respectively. Divisible by 2 3 5 and 7 respectively. Okay, therefore the number of primes less than 100 is equal to 4, these 4 primes, plus n of p1 dash, p2 dash, p3 dash and p4 dash. N of p1 dash, p2 dash, p3 dash, p4 dash is nothing but the number of elements which are not divisible by these primes 2 3 4 and 2 3 5 and 7. Okay, since we have to eliminate all the multiples of these numbers. Okay, and as here we have to find out the number of primes less than 100, as here we have to find out the less than 100, then this capital N is here 99. Okay, since we have to find out the number of primes which is less than 100, therefore we can't take 100. Okay, therefore according to the definition of principle of inclusion exclusion, n of p1 dash comma p2 dash comma p3 dash p3 dash comma p4 dash is equal to n of p1 minus n of p2. Here there is no need to take sum. N minus n of p1 minus n of p2 minus n of p3 minus n of p4 minus n of p1 p2 minus n of p1 p3 minus n of p1 p4 minus n of p2 p3 minus n of p2 p4 minus n of p3 p4. Now we have to take the plus one. N of p1 p2 p3 plus n of p1 p2 p4 plus n of p2 p3 p4, sorry, p1 p3 p4 p1 p1 p2 p3 p1 p2 p4 p1 p3 p4 plus n of p2 p3 p4 minus n of p1 p2 p3 and p4, where this n of p1, for example, n of p1 is nothing but the number of, here p1 is nothing but 2, p2 is nothing but 3, that is the number of elements which are multiples of this p1 is 2. Okay, therefore n of p1 is nothing but number of elements which are in the multiples of 2. N of p2 is nothing but the number of elements which are multiples of 3, number of elements which are multiples of 5, and p of p4 is nothing but the number of elements which are multiples of p4. Now n of p1 p2 is nothing but the number of elements which are in the multiple of both p2 and p1 and p2, that is 2 and 3, that is the number of elements which are in the multiples of 2 and 3 is nothing but the LCM of 2 and 3, which is equal to 6. So either we can find out the number of elements which are multiples in 2 and 3, or we can find out the number of elements which are in the multiples of 6, then both are same. Okay, similarly all of them. Okay, now already here we know the value of this capital N, which is equal to 99. Now we have to find out the number of elements which are in the multiples of this p1, which is equal to 2. Therefore n of p1 is equal to, now how we find it? By using the greatest integer definition. Okay, and this concept is we have already seen in number 3. Therefore n of p1 is nothing but greatest integer of 100 divided by 2, and which is nothing but 50. Okay, similarly n of p2 is nothing but greatest integer of 100 divided by 3, and which is equal to 33 point something, and by definition of greatest integer which is equal to 33. N of p3 equal to 100 divided by 5, and which is equal to 20. N of p4 is equal to 100 divided by 70, and which is equal to 40. N of p1 which is equal to greatest integer function of 2 and p1 is 2, that is here we have to take 2 and 3, that is LCM of 2 and 3, which is nothing but 2 into 3. Okay, now next one is which is nothing but 2 into 3 is 6. So 60. N of P1, P1, P2, P1, P3. P1, P3 is equal to 100 divided by P1 to P3 5, which is 10, which is equal to 10. Similarly, we can find out for remaining all of these. 2 and 7, 7. Let us take this one as. Find out the corresponding values. N of P1, P4 is equal to 7. N of P2, P3 is equal to 6. N of P2, P4 is equal to 4. N of P3, P4 equal to 4. Sorry. N of P2, P3 equal to 6. N of P2, P4 equal to 4. Okay. N of P3, P4 equal to 2. N of P1, P2, P3 equal to P1, P2, P3 is equal to 3. N of P1, P2, P4, P2, P4 equal to 2. N of P1, P3, P4, P1, P3 and P4, which is equal to 1. N of P2, P3, P4, P2, P3, P4 equal to 0, and N of P1, P2, P3, P4 is again 0. Now we have to put all these values in this equation 1. Then we get N of P1 dash, P2 dash, P3 dash and P4 dash is equal to 99. N equal to 99 minus. Now we have to take this 50 plus 33 plus 20 plus 40. 50 plus 33 plus 20 plus 40. Okay. Plus this one 16 plus 10. 16 plus 10 plus 7642. 7642 minus 3210 minus 3 plus 2 plus 1 plus 0 plus minus plus minus plus sorry minus this one plus this one minus this one plus 0. Okay, so which is equal to 99 minus 55 plus 33 83. 83 plus 20 83 plus 20 103. 103 plus 14 107 plus 170. Okay, plus 16 plus 20, so 16 plus 10 26. 26 plus 7 33. 33 plus 6 39. 39 plus 4 43. 43 plus 2 40. 5 minus 3 plus 2 plus 1 6, which is 0. This is equal to 45 plus 99, which is 144 minus 117 plus 6 123, which is equal to 4 minus 3 1, 4 minus 2 2, and which is 0. Therefore the number of primes which are in between 10 to 100 are 21. Therefore the number of primes number of primes less than 100 are equal to 4 plus 21 and which is equal to 25. These 4 are nothing but 2, 3, 4 and 5, and these are the primes which are in between 10 to 100. Okay, therefore the total number of primes which are less than 100 are equal to 25. Thank you for watching the lecture.